Good evening everyone, I am Mr. Ish. I hope everyone's doing well. Here in this video we're looking at why amides are special. Before we look at exactly the answer to this question or this rhetorical question, let's look at how we can generate an amide. Then we will examine the functional group. We are starting here with an acyl chloride, which is a carbonyl compound with a chlorine atom over here. Pay particular attention to these electrons, which are lone electrons. I have a chlorine over here with these many electrons, the oxygen with that. When you're looking at this compound, you know chlorine is electronegative, oxygen is electronegative. The dipole moments are sucking the charge away and making this carbon relatively partially positive or starved, meaning it is charge deficient. Because of its charge deficiency, we have here an amine. We'll say RNH2, and you know amines have, or the nitrogen has, a lone pair of electrons, meaning 2 electrons, which enable this to act as a nucleophile or a Lewis base, an electron pair donor. It's looking for an electrophilic site, and the carbon is just that. When you look at it, it attacks it over there, and what you end up seeing is this. By this attack, you're seeing a rearrangement of electrons. This double bond will break and will shuffle some electrons back to the oxygen, and you'll see it as this. I have this. I'll have now 6 electrons. Here you have 4, but now you have 6 because the double bond is broken and returned 2 electrons back to oxygen. You have this nitrogen, you have a hydrogen, you have a hydrogen, you have this R group because this is an amine. R means rest of the molecule. Then you have this chlorine as you see right here. Now let's bring in the charges, and this is what we have. Minus on the oxygen, positive over here. Now what we will have is a halogen. A halogen is a good leaving group. It likes to leave the molecule in the presence of a other compound, which is your nucleophile, coming into play. These 2 electrons will return back to regenerate the double bond. This chlorine will go away. When you look at it, what will happen is this. You've regenerated the carbonyl compound. You have the nitrogen, you have the hydrogen, you have a hydrogen, and you have the R group, but you still have the positive charge. What will happen over here is the nitrogen bond will break away. The 2 electrons of this will come back into the nitrogen to regenerate its lone pair of electrons. The hydrogen will go away. When you're looking at it, your end result is your amide functional group. You have R, carbonyl, you'll have your N, here a hydrogen, your R group, and your 2 lone pair of electrons, plus your proton, which has drifted away. And this right here will be the reaction by which the amide is generated. This right here is an amide, a nitrogen bonded to a carbonyl carbon, and that right there is your amide. And you can say this right here, this carbon nitrogen, is your amide bond. This is how we generate it from an acyl chloride, which is the easiest way. And this right here is an acyl chloride. It comes from acetyl chloride, but it's an acyl chloride. What you have over here is a functional compound, which is R, C double bond O, and an X, where X is a halogen, and that halogen here happens to be a chlorine. It's an acyl chloride in the presence of a nucleophile, which is your amine, will give you a amide. Now let's talk about why these compounds here are special. This here is a representative amide. You could have had another R group, you could have had 2 hydrogens, it doesn't matter, but this right here is an amide. This here particularly is called your amide bond, your carbon nitrogen. Let's talk about what makes this compound special. You know it's a carboxylic acid derivative. It's the least reactive carboxylic acid derivative. And why is that the case? When you're looking at this compound, you have a carbon over here which is going to be charge deficient because it's attached to 2 electronegative atoms. One is nitrogen, one is oxygen. If you were to look at the dipoles, you're sucking it away in the following manner, and this is charge deficient. But unlike the other type of carbonyl carbons which are charge deficient, you have 2 electrons here which have the ability to go back and replenish this charge. By replenishing it, this charge deficiency is not as great as one would expect. Keep that in mind as well. Now look, we have a compound over here which has potentially 2 Lewis bases. This right here, the oxygen, has the ability to donate. It has the potential to donate its lone pair of electrons, so it's a Lewis base. This nitrogen has the potential to donate its lone pair of electrons. It is a Lewis base. But from both of these, the nitrogen has a greater tendency to be a Lewis base, so it will always act as a Lewis base in favor over an oxygen. Oxygen will take the back seat, nitrogen will take the front seat, and will always act as a Lewis base in this type of compound. Now consider the resonance structures that can play about. When the nitrogen can act as a Lewis base, it can donate its electrons over here, and you can have a shuffling of electrons. And when you do that, look what you end up seeing. You end up seeing a compound which develops like this. Oxygen has developed 6 electrons around it along with a negative charge. You have developed a carbon-nitrogen double bond, and you have a hydrogen, you have a R group, and now you've developed a positive. When you look at this and you're seeing the shuffling back and forth between these two resonance structures, you end up seeing a generality come about. What is that generality? It's this. Let me draw it for you. You're looking at something which looks like this. Here's your hydrogen, here's your R group, here's your nitrogen. You're looking at something which looks like this, which means it's an intermediate resonance structure, or perhaps the most accurate resonance structure between both of these, where you have the potential of a double bond sweeping its way across from oxygen, carbon, and nitrogen. I'm not showing you the charges, I'm just showing the combined effect of these resonance structures is this. You're looking here, because it's still neutral, you're looking over here at something like this. You have in essence sp2 hybridization, sp2 hybridization, and sp2 hybridization playing around and playing about with nitrogen, carbon, and oxygen. In essence, you have a double bond running all the way across. It makes it relatively stable. Look at this and remember it. And now let's talk about why the amide is special. It's special because it is the least reactive of your carboxylic acid derivatives. It's the least reactive. It's least reactive because this right here, this entire group, I'll circle it for you, is a pore leaving group. It will not have a tendency to go away. If you were to consider this as charge deficient and you brought in a nucleophile and you were to attack it, that nucleophile will attack, you'll have a shuffling of electrons, but the nucleophile might go back out because this will not want to leave. It's a pore leaving group, so the amide bond will retain unless you change the reaction conditions to make it very strongly acidic or strongly basic, high temperature, high acidity, high basicity, all of that, bringing that into play. Then you could push this out, but generally it doesn't want to be pushed out. It's a pore leaving group. I've already shown you the resonance. The other thing is the resonance, this resonance structure that you're seeing, what it ends up doing, it eliminates this charge deficiency and it stabilizes carbon, and it ends up making it less reactive. By stabilizing the carbon atom, you've made this a poor electrophilic site, and a nucleophile is not likely to come over here. The resonance structure, the two electrons, the lone pair of nitrogen, will stabilize this carbon by means of its resonance structure. These are perhaps the two most important things you need to know. One, the amine group, primary, secondary, tertiary amine, whatever it might be, is a pore leaving group, and the resonance comes into play and it stabilizes this carbon atom. And you're thinking it's partially deficient, you might as well remove it and think it's not a very reactive site. These electrons will come over here and stabilize the charge deficiency of this carbon and make this a less reactive site. In general, amides are very less reactive. What I've put for you over here is an additional item you can remember, which comes into play. These lone pair of electrons stabilize the carbon by delocalization of those nitrogen electrons. When you can shovel these electrons around or spread them around like I was showing you, it's called delocalization of those electrons. They're being delocalized from their initial site and they're spreading their effect elsewhere. By spreading their effect elsewhere, they're stabilizing the entire molecule, but in essence they're stabilizing a charge deficient carbon and making this less reactive or less potential site. Because of the stabilized carbon and the delocalization of the nitrogen electrons, what you end up seeing or needing are harsh conditions to make a amide reactive, otherwise it will remain unreactive. And that right there will be the end of this video. Thank you for watching.